Howdy everyone, and welcome back. And this is going to be a shorter but really focused video on RC circuits, so circuits with resistors and capacitors. And so some interesting things happen with these kind of circuits. Most of the circuits we've been talking about so far have been direct current circuits. These will be too, but they're not time varying. They're the same thing forever and ever, and nothing really ever changes. But for here, we're going to have to actually have a time component, because it turns out capacitors in these sort of circuits don't stay the same forever when you couple them with resistors. So what do I mean? So imagine here I have a capacitor and it's not doing anything, and then it gets plugged into a circuit. Then it has some potential difference over it. So charges want to start rushing onto it and then moving off of it. So over time, I'm going to get a bunch of positive charges and negative charges on this side. So what does that mean over time? Well, initially this thing is going to be acting like a perfect wire. So recall, charges actually aren't moving over this thing. It's just this electric field that goes and pushes charges away from one side and towards the other side. So eventually this is going to start filling up with a ton of charges and ton of charges and ton of charges until it hits this maximum capacity, this Q equals VC limit. So initially it's like this perfect wire where it's moving charges away on this side, moving this charges, even though they aren't really crossing, but it is moving charges in relation to the whole circuit. So there's no resistance effectively, there's no voltage being dropped here, but eventually it gets so full that it can't move any more charges with the amount of voltage it's been given. So eventually it goes from being a perfect wire to this broken wire where nothing is happening over it, because again, no charges can really cross over it, and it's got the max, so effectively can't move anything. So this is going to have a lot of interesting applications in circuits. We're going to just go over some really basic examples to give you a flavor of what's going on. So let's go over an example where everything's in series and then an example where everything's in parallel. Hopefully that gives us a good flavor of what's going on. So in this problem, we have everything in series. The switch is initially turned off, so there's nothing going on. And then we're going to turn it on. We're going to combine and complete the circuit. And so imagine what happens. The charges start moving and they start hitting this capacitor. So it has no charge on it, then fills up with charge, and at some point can't move any charges, and the circuit eventually turns off. Well, there's nothing passing over the resistor, but so you just maximize the energy and all the charges on this capacitor instead. So we want to figure out a few things here. We're going to find this time constant. That's really a constant referring to how often things change, and it's really going to be regards to this overall function we care about. So we are actually able to write down the charge as a function of time. So again, the charge on this is not some static Q equals VC. It's really dynamically changing depending on the time that we're looking. So it's a function of time, so there's a maximum, but it goes also from a minimum to this maximum. So we can really derive this equation using Kirchhoff's laws and calculus, but we're just going to say that it's true. So we get this 1 minus e to this negative exponential. So what does this look like? Well, we can write out a graph, and effectively this looks like at some point we have no charge, and that's what's going on in the beginning. Nothing is happening, nothing's sitting on it. When we have this maximum charge, Q max, then we have something that's decaying to this maximum charge, so it asymptotically reaches this maximum. So this goes to zero eventually over a long period of time, but it just eventually goes to this maximum charge. So you can imagine as this charge is changing, we're gonna have some current going through the circuit, and eventually it's gonna hit some maximum. But as far as this question goes, this time constant tau is just RC. That's something that we get when we derive it. So we know the resistor, we know the capacitor, we can do this with any problem. So the next question, what's the maximum charge on C when the switch is closed? So you can imagine over a long period of time, all of the charges have accumulated here. This is at some maximum. So at that point, there's no current, there's nothing going on it. So this effectively doesn't matter. So it's essentially, this is just the same voltage as the battery that's supplying it to it. So we can just use Q equals VC. We do that, we get the voltage of the battery times the inherent capacitance of this capacitor. So maybe we're interested at current at a certain time. So we can actually solve for that using a few different things. So we have our charge rule, we're going to use that, but then we're also going to use Kirchhoff's laws. So we can write down the current as at this certain time. Again, we have current as a function of time. All we need to do is put in for t, we put in 10 seconds instead. And so we can go and do that. Okay, we have the current at that time. Again, put in any R and C that you want, any epsilon that you want in terms of the voltage of the battery. And then we can actually find, we'll use this in a moment, we can actually find the voltage over that capacitor. So then we use Q equals VC. We solve for this V at any time. Okay, it's the charge at that time over the capacitance. So how do we get to the current? Well, we need to use Kirchhoff's loop law. So again, recall in any loop, the voltage, when we add it all together, has to go to zero. And so that's going to imply that the voltage of the battery has to get dropped over these two components, the resistor and the capacitor. So again, I'm going in a loop. I had to go to 0. I add some voltage here, which means I had to drop it between these two. That's the only place the energy can go. So we write that down. We can write down the voltage for each of these things. So again, we have an expression for VC. It's a little convoluted, but for the resistor, it's just V equals IR. And so we need to solve for the I here. We need to get this I. That's our goal at the moment. Okay, so we subtract this VC to the other side. That's what's going on here. We divide out this R to move it over. And we have this expression for VC, because again, we wrote down this Q over C, and then we have this Q expression. So this is all I'm doing is combining these two and putting it in for VC. And it's a little bit of a complicated expression, but some interesting stuff happens. So this extra term, this one term gets canceled out here. It gets subtracted off when I distribute this epsilon into the rest of the equation. So all I'm left was essentially V equals IR in a kind of way with this functional dependence on time, this exponential decaying. So if it was at the current maximum, this thing would just be 1, and we would just get V equals IR. That's really what this is saying. But I have this component that's exponentially decaying over time. So what does that mean? So if I draw a graph of the current over time, this is time. It's at some maximum here, given by V equals IR, and then it's exponentially decaying to 0. So why would that be? So again, when I open this up, this is acting like a perfect wire. It's easily moving charges all the way through here, but eventually it gets full of charges. It can't actually move them anymore. So I have a ton of current going through here because this is the only thing causing any voltage drop, and effectively has resistance. But eventually this is an infinite amount of resistance. Everything is being dropped over this thing. So then there's no current passing through. This is completely stopped at all. And so I go to 0. That's all this is saying here. It's falling as an exponential decay. So let's just finish and do the same problem, but now in parallel. So imagine here, I am charging a capacitor here. I have some switch that's connected to A. And then when this is fully charged, I go and move it to B. And then you can see that this is going to be creating a current here. This is going to be supplying energy, creating current, moving charges, but eventually it's going to use up all of its energy. It's also going to go to 0. But let's figure out how it does that. So we can find the current as a function of time. So really how we do that is we use calculus and Kirchhoff's laws, but we're going to kind of skip that. So we can find that it's going to be an exponential decay, not the 1 plus, but just a simple exponential decay. So it's, again, this thing is fully charged up. It's at some Q max in the beginning, and then it just exponentially decays to 0. So it expends all of its energy, all of its charge out. Again, from the last problem, we found that Qmax is just going to be epsilon c, and we found what this time constant is going to be. It's just going to be RC. So we can do a similar thing to find the current as a function of time. We can still use Kirchhoff's laws, except this time the only things we have is going to be the capacitor and the resistor. So once I close it, and this is the circuit, again, this is a broken wire here. None of this stuff matters anymore. It's just these two components. I go in a loop. This is adding some voltage. This is taking away. That's all that's happening here. So I write that down. I write that down with Kirchhoff's loop law, and we can go and solve for the current. So we can go and write down the voltage over the capacitor using Q equals VC. We can write down the voltage of the resistor using V equals IR. We go and we can then solve for this I by dividing the R, well, subtracting to their side, and then dividing by the R. And then we get this thing. Oh, there's an error. This is a C here. There we go. You go and take this expression, put it down here, the C's cancel. So then we're left with this constant out front is just I max. Again, it's just V equals IR, but I'm given this exponential decaying. So again, the same thing is happening here. The current, just compared to the last problem, is also exponentially decaying. It's not going to some maximum. It's also like the charge dying over time. So this capacitor is supplying energy to the circuit. It's creating a current. This resistor is taking that away, and eventually all of that energy will go away. The current will go to 0, the charge in this will go to 0, and then it'll just be boring. There'll be nothing happening anymore. That's all we're saying with this sort of problem. So just a couple questions, pretty quick, but hopefully it gets you start at looking at RC circuits and direct current situations and how essentially just capacitors die over time. That's pretty much the only thing we're getting away for this. But thanks for joining. Appreciate it, you being here. Okay, thanks, bye.